How's it going, everybody? Yeah, I got this really weird colored shirt on today. As if you think back, you're probably watching this, next week in my time right now. But if you think back to last, what day is today? Thursday. There, I have no sense of days. It was pouring down rain all day, and I had looked at the radar, and there was only like one line of storms, and I was like, oh. It's only sprinkling out. It looks like it's past us. I'll go for a run. Yeah. Yeah, it wasn't just one line. Yeah. And I think the line, like here, if we were like right here, the line was like moving up, like we were going to just stay in the rain. And I didn't even realize that. So I got soaked. And so, like, this was like the only shirt that was like on top. Okay, enough storytelling. Okay. This is section 13.4, inverses of trig functions. This is probably going to be a longer video, I'm thinking. But this whole week is dedicated to section 13.4. Just so we know, we will have a quiz on 13.4 next week. We'll review and then quiz next week. And then we'll do section 13.5 and 13.6 to finish out the year. All right, let's get to it. All right, so, in thinking about the trigonometric functions, we have sine, cosine, tangent, secant, cosecant, cotangent, right? All of those ones. What does it mean to be inverses? Okay, what does it mean to be inverses? Well, remember, an inverse undoes the other thing, right? Like if you think about what's the inverse of an x squared? It's a square root. What's the inverse of taking something to the exponent? It's a logarithm, right? It undoes those things, right? So what's the inverse of a trigonometric function? Well, remember that, like when we started this, we had like the sine of theta is equal to, I don't know, some decimal, 0.5, 1/2, right? And we said, okay, sine of, and we could have said, well, what is, well, that's what we'll figure out today. How do we figure out what that angle is, right? That's really what we're looking for. In this whole lesson, section 13.4, it's all about how do we figure out what that angle is, okay? That's what we're going to be looking at here, okay? Now, this is going to be a long video, but the next video, the second day of this week is really just going to be, going over the key concepts and then giving you another assignment, okay? So this is going to be a longer one, but the next one's not going to be too bad. All right, so we've evaluated trigonometric functions for a given angle. I've given you the angle before. And then I've asked you to find the sine value for it. I've asked you to find the cosine value for it. I said, what's the cosine of, pi over 3? And you could figure that out. We just did that. I could say, what's the sine value of 60 degrees? And then you would do that. And you'd figure out what that is, But now we're looking at what is the angle when you're given what the sine value is actually. Okay, so to do that, we need to use an inverse trig function, inverse trig relation, right? So how would I, basically get theta alone here? Well, to the other side, I would have to do the inverse of sine. So inverse sine of A is theta, inverse cosine, inverse tangent, okay? So now, please don't mistake these to the -1 powers as any sort of reciprocal value. That is not the same thing. Okay, we learned what the reciprocal values were. The reciprocal values were, cosecant, secant, and cotangent, right? That's not the same thing here. Inverse cosine is not the same thing as secant. That's different. Just the notation looks a little weird, okay, because it's the inverse of that thing, right? Okay, so now in thinking about this, if I asked you, we should have our unit circles out. So if you don't have unit circle out, you should get it out. Just to look through. If I asked you, well, let's go back to this. The sine of theta is 0.5, right? Can you find an angle? Can you find a theta where the sine value is 1/2? Well, what is sine? Sine is the y value of the coordinate, right? So find an angle given that the y value is 1/2. Go ahead, look for it. I'll give you some time. Some of you guys, oh shoot, I messed it up. I wanted to say cosine, whatever. Some of you may be thinking, well, I found 2 of them, right? I found 2 of them. There are actually more than one spot that has that on on the unit circle. Okay, let's switch to cosine. What if I said cosine of theta is 1/2? Look for, now remember the cosine is the x value of the coordinate, so look for an angle where the x coordinate is 1/2. Well, you're going to find that there are two different spots on the unit circle that have that 1/2 as the x value. Okay. So what does that mean? That means that there's actually two different solutions to this equation, this inverse cosine of 1/2 is equal to theta, right? Just if I get the cosine over to the other side. There are actually two different solutions to this equation. Pi over 3 and 5 pi over 3 in radians, obviously. If we wanted to give it to me in degrees, it'd be 60 degrees and 300 degrees, right? So there are actually two different locations that actually happen at. But in actuality, what about, say this is 60 degrees, right? What about 420 degrees? Wouldn't that end up at the same spot? Just going whoop, 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 right? What if I add another rotation? What if I added another rotation? See what I'm getting at here? All coterminal angles will end up at this same spot, which has the same cosine value. All angles with the same reference angle will have the same sines, cosines, and tangents. Just you have to apply the quadrant rule that we learned, this whole positive, positive, negative, 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 and positive, negative thing to it. But if they end up in the exact same spot, they're going to have the exact same sines, cosines, and tangents, right? This, 60 degrees or 420 degrees. Where am I getting 420? 360 plus 360. Right? If I added another 360, that would end up at the same spot. Another, they would all have that same value. So it's not just two answers. It's actually going to be an infinite amount of answers. Couldn't I go in the negative rotations? What about, a negative 300 degrees? What about a negative more than that, negative 660? That would also end up in the exact same spot. So there's actually an infinite amount of coterminal angles that we have. So there's an infinite amount of solutions to this equation. Weird, right? Weird. Now that means we have to use some sort of special notation. So I ask you now, find an angle measure. Look at your unit circle and find the angle measure where the cosine is radical 3 over 2. So again, since this is cosine, you're looking for the x value. Find the locations where the x value is radical 3 over 2. So I'm going to go to my unit circle here, and I want to find, let me actually make this a little bit smaller. Okay, there we go. Fit it all on one screen now. I'm going to find where the x value is radical 3 over 2. Okay, found it. X value is radical 3 over 2. Found it. Okay, so does it tell me to do degrees or radians? Let's just check. Find all possible values. Well, let's do both. Heck, why not? Okay, so I'm at 30 degrees and 330 degrees. 30 degrees and 330 degrees. 30 degrees and 330 degrees. Okay, what is that in radians? That is pi over 6. And I think that's 11 pi over 6. Yeah. Okay, now, so we know we have two solutions to this, but we also have to take care of all coterminal angles. It says find all possibilities, right? So I'm going to say plus all rotations, 360n. What does that mean? That means I can just keep multiplying. I can say plus 360, plus 360, plus 360, plus 360, where n is just some value, some integer value, okay? And we have to say that for both things. If I was very, very picky, I would say where, where n is an integer, right? Where n is an integer. Well, how would I take care of all rotations here? Well, if it's in radian form, well, then I would say plus 2 pi. That's a full rotation times n, however many rotations that I want to use, okay? Where n is an integer. That's an element of symbol, element of an integer, okay? Okay, so let's talk about this. This piece right here, I don't really need that. Just know that that's what we're talking about with that n value. We're just saying all possible values of n. Now, why am I not saying minus? Why can't I do like a plus or minus right there? Well, I don't really need to. That's kind of almost too much information, because I could be subtracting, right? I could be subtracting each rotation, but if I consider n to be an integer, that takes care of all negative numbers, which if I multiply by a negative number, it turns into a subtraction sign. So I don't even really need to worry about a plus or minus there. I can just say plus. All right, inverse tangent of 1. Okay, now tangents are a little funky because it's not just y, it's not just x, it's actually y divided by x, okay? Now, think about all of the tangents along the unit circle. All of the tangents, hopefully you noticed this from this worksheet that you actually just turned in today by my timing, Thursday night. Think about that worksheet that you did last week. You should have been noticing that the tangents were all the same for each family, okay? And then you just had to apply that, those the signs, SIGN signs to it, right? So thinking back to, the tangent value, since tangent is 1, right? Y divided by x is going to be 1. Well, what kind of thing gets you y divided by x getting you 1? Well, that would mean if these two values were the exact same. So what points along the unit circle have the tangent of 1? Oh, or have the coordinates that are the exact same? These guys here, right? Now, you may be thinking, whoa, 4 answers. No, not 4 answers. Positive divided by negative, that would end up being a -1. Positive divided by negative, or negative divided by positive, that would end up being a -1. So the only places where tangent ends up positive are the first and third quadrants, because those are where the signs are the same. So y and x have the same sign, so they would end up being positive. So there are 2 locations here, the 45 and the 225. Okay, 45 and the 225. Let me get back to here. So 45 degrees and then the 225 degrees. Okay. Now, what is that in terms of radians? That's pi over 4. And then 135, I think it's 5 pi over 4. 6, 7 pi, yeah, that's right. And then now let's account for all rotations. Plus 360n, plus 360n, plus 2 pi n, plus 2 pi n. Okay, that accounts for all rotations. All right. Because more than one value of theta produces the same output, it's not a function, right? If I say, what are the answers to this? What are the answers to this? Well, there's an infinite amount of solutions there, right? That's not how we write it, but there is an infinite amount of solutions. So it's not a function, right? One input value gets an infinite amount of output values. So it's not a function. So what if we really wanted it to be a function? What if we really, really wanted it to be a function? Well, then it would be necessary to restrict the domain. We would have to say, well, then you can't have all of those answers. You can only have one answer to be a function, only one input, or sorry, one output for each input. So what we're going to do is we're going to restrict the values, okay? Trigonometric functions with restricted domains are indicated with the capital letter. What? So you mean to be telling me that all along we were writing sine like this, and I didn't really tell you yet, but it was supposed to be lowercase. Cosine, and then tangent. These were all supposed to be lowercase letters, because if you actually make it a capital letter, you're saying something a little bit more, well, it holds a little bit more weight to it, okay? What does it mean when you capitalize the sine, cosine, and tangent values? Well, it actually means you're turning it into a function. It means that you're restricting the domain. Okay, now how are we going to restrict the domain? Well, for sine, we're going to restrict it to the first and fourth quadrants. For cosine, we're going to restrict it to the first and second quadrants. And then tangent, we're going to restrict it to the first and fourth quadrant. Why? Because the sine values, think about the y values. If I picked a point right here, where's the only other point on the unit circle with that same y value? Right here. So if I only wanted one of those answers, let's pick that one. I would discount the left side, right? So what about here? Where's the only other place along that unit circle? That would be down there, over here. So only one solution is going to come out, okay? Think about cosine. Look about x values. Say I had the x value right here. What's the only other place on the unit circle that had the same x value? Down here. It would have the same y value, but it would be negative in that case, right? So therefore, I'm only going to be using the first and fourth quadrants. So therefore, that answer goes away. I'm only using this answer. Think about tangents. we just did an example where that we had the tangent here. The only other corresponding tangent was down there. You're going to notice that that happens in opposite diagonal quadrants. So like these quadrants are going to have the same tangent values, and then these quadrants are going to have the same tangent values. So if I only wanted one answer, I'm going to restrict it to only the first and second quadrants, or sorry, excuse me, the first and fourth quadrants. Now, we have to be a little bit picky about how we write it, because, think about this. If I wanted to say, well, how am I going to restrict it? And you wanted to say, okay, I only want angles that are from the fourth quadrant and from the first quadrant. So we would say, okay, I want to restrict it from 0 to 90 degrees, but then I want to pick it back up at 270 degrees and then go to 360 degrees. Okay, that's not really eloquent, right? That's not really nice to say. We want one complete statement. What's another way to say 270 degrees? Negative 90 degrees to positive 90 degrees. And we can say that. We can go from negative 90 degrees to positive 90 degrees. And that's what they're saying here, just in terms of radian measure. Okay, well, I don't need to do anything special for cosine because I can just say 0 to 180. Okay. But tangent, I do have to do the same thing, negative 90 degrees to positive 90 degrees. Now, you're going to notice here, why am I not using or equal to's? Why am I not using or equal to's? Think about this point down here. 0, negative 1. What is the tangent of that point? Y over x. Oh, that point down here and that point up here are actually undefined. So I'm never actually going to use negative 90 or 270, or I'm going to use positive 90 because remember, that's 0, positive 1, right? So that would be y1 over 0. No, can't have that. So I make note that there's no or equal to's there, okay? I'd write that down. That's pretty important. This is just another kind of summary to that. Yeah, I don't even know why I have this slide on here. You don't really need this, actually. I think the reason why I have I do know why I have this on here, is because the output values are given in both radian and degree here, right? So the input values, the domain values, and this is, okay, whatever. This is good. Thinking about what can I plug in? What can I plug in? Like, what numbers can I plug in for this a value? Well, the numbers that I can plug in, think about the possible sine values I was getting out. Like if I go look back at the unit circle, what y values do I possibly get? What's the biggest and smallest y value that I could possibly get? Well, the biggest y value I get, if this is a unit radius of 1, is 1. What's the smallest y value I get? Negative 1. So my y values will go to and from, I don't want to say range because that's domain and range again, next up here. It will span from negative 1 to positive 1. Think about the x values. Left to right, this again spans from negative 1 to positive 1. Okay. Now, if you think about the tangent values, though, think about the tangent values. If I keep taking y divided by x and y divided by x, I'm not going to get just negative 1 to positive 1. I'm actually going to get negative infinity to positive infinity. Okay. So therefore, the tangent is not unrestricted within the domain. Okay. All right. Oh yeah, good. I'm glad I have this in here. The inverse trig functions are also known as arcsine, arccosine, and arctangent. Sometimes they're written as this, okay? Or sometimes I've seen them as this, right, with an H there. Yeah, that's also arcsine, arccosine, arctangent. I don't know where that notation comes from, but if you ever see that arc, like sometimes they use that in like an ACT, like what is the arc sine of this? That's just inverse, well, sine, whatever. That's just inverse sine, inverse cosine, inverse tangent. Okay, so if you ever see that or this, that only is shown in like higher level stuff though. But I've seen this in weird places before with the arc there. Yeah, that just means inverse. Okay, all right. So evaluate each trigonometric function, give your answer in both radians and degrees. Okay, now look, capital C cosine. Capital C cosine is restricted to only the first and second quadrants. So where I may get answers down here, since you see a capital letter, you know better now. You know that this is only one solution. So where is that solution? Where's the x value with negative radical 3 over 2? Well, the x value with negative radical 3 over 2 is, let me get this out of the way. Okay, where is it? Where's the x value of negative radical? Oh, found it. Right there. Okay, now you may say, oh, but I see it down here. Well, the cosine gets only restricted to the first and second quadrants. This goes away because I want it to be a function. So all of the solutions down there are gone for cosine. So this is the only one that I want. This is 150 degrees or 5 pi over 6. 150 degrees or 5 pi over 6. 150 degrees or 5 pi over 6. Do I need to do that plus 2 pi n or plus 360 n? No, because it's capital letter. There should only be one output. I know I'm writing two things, but it's just written in different ways, okay? It's like saying, 1 yard or 3 feet. That's the same thing, right? It's just shown in two different ways. All right, let's keep going. Inverse sine of 3 over 2. Now this looks a little deceiving there. You might be thinking, well, did you just accidentally write, forget that that's a radical 3 over 2? Like, did you screw up, Mr. Library? No. Do you see anywhere along the unit circle that has a 3 over 2? Not a radical 3 over 2, a 3 over 2. No. Is it even possible? Well, that's inverse sine of 1.5. Is that possible to get? Are there any angle measures that have a sine value, a y value, bigger than 1? No. The highest sine value I have is positive 1. Doesn't even go up higher than that. Okay, let's try to find inverse sine of negative radical 2 over 2. Okay, all right. So go to my unit circle, find where the y value, I know it's a y value because it's sine. And I know since it's capitalized, I want just the one place. Now think about where is it restricted? First and fourth. Okay, so negative radical 2 over 2. First and fourth quadrants. Let's find it. There. Right? The y value is negative radical 2 over 2. Again, I see it down here, but I'm not going to circle that answer. That's not right because I only want answers here and here. Okay, so where is this? 315 or 7 pi over 4? 315 or 7 pi over 4. However, think back to the restrictions. The restrictions are negative 90 to positive 90. Is that within there? I know, like, location-wise, it is, but numerically, is 315 a number in between negative 90 to positive 90? No, but there is a coterminal angle that exists here. Okay, so what is equivalent to? What does that mean? Well, 350 degrees is actually equivalent to negative 45 degrees. And is that within the domain? Yes. Negative 45 degrees. That is the coterminal angle that matches that. Or, in other words, negative pi over 4. And that's the true answer. Because it's got to fit within this domain. Has to fit within that domain. All right. A painter needs to lean a 30-foot ladder against a wall. Safety guidelines recommend that the distance between the base of the ladder and the wall should be 1/4 of the length of the ladder. To the nearest degree, what acute angle should the ladder make with the ground? Okay, let's draw ourselves a picture. Okay, here's my ladder. Yikes, really good ladder, folks. Doesn't even connect to the other bar. Here's a wall that we're painting. Sure, building, whatever. Okay, so this is a 30-foot ladder. I want to know, safety guidelines recommend that the distance between the base of the ladder and the wall should be 1/4 of that amount. So let's take 30 divided by 4, 7.5 feet. That's at least 7.5 feet. So what angle should the ladder make with the ground? What should my theta be? Well, what do I have here? This is the adjacent side, and this is the hypotenuse. So what's the only trig ratio that deals with adjacent and hypotenuse? It's cosine. So we know that the cosine of this theta, now I should make that a little bit more capitalized, but cosine of this theta is the adjacent side over the hypotenuse side, so 7.5 over 30. So that means theta is going to be the inverse cosine of 7.5 over 30. Okay, these are the more geometric problems that that you've worked with, probably last year when you did these trigonometric ratios in geometry. But okay. So now obviously I'm getting on my calculator. Now is the time I go to my calculator, because is there a place on my unit circle that's 7.5 over 30? No. So let me get this out of the way. I'm going to do inverse cosine, and I just hit second cosine. Inverse cosine of 7.5 divided by 30. 75.5 degrees. Theta is 75.5 degrees. Now thinking about this, actually, let's go back to that. Because I just put in 7.5 over 30, but what if I took the intermediate step there and actually showed this? Okay, 0.25. So theta is going to be equal to inverse cosine of 0.25. Now, think about that along the unit circle. I know I don't have a 1/4 on any of my coordinates, but if I had a cosine, an x value of 1/4, an x value of 1/4, this is 1/2, and this is 1, right? So maybe somewhere right in here. I want to know what place along the unit circle has the cosine of 1/4. Right here. What kind of angle do you see right here? Oh, is that about 75.5 degrees? Yes. Okay, so that's really what we're looking at there when you find that theta. Okay. All right, let's try another one here. A group of hikers wants to walk from a lake to an unusual rock formation. Interesting. The formation is 1 mile east and 0.75 miles north of the lake. Okay, so here is the lake. There's a lake. It's green, whatever. The rock formation is 1 mile east and 0.75 miles north. Okay, here's my rock formation. Okay, kind of looks like a fist or something. I don't know. So it's 1 mile north and 0.75 miles east, not drawn to scale. Okay. What degree, in what direction should the hikers head from the lake? Really asking what's my angle there. Right? We know that makes a 90-degree angle. So what am I looking at here? This is the opposite. This is the adjacent. So tangent of my angle. And I actually should capitalize that now, because I only want one answer, right? I'm not going to have more than one answer. Tangent of theta is going to be equal to the adjacent over the opposite. Oh, whoa. No. The opposite over the adjacent. Excuse me. Yikes. Late, folks. The opposite, 0.75 over the adjacent 1. Okay, so theta is going to be equal to 0.75 over 1. Oh, sorry. Oh, geez. Inverse tangent of that. Did you see? I almost tried to write that. I almost tried to squeeze that in there. Right. There's theta. Okay, so let's do that. Inverse tangent. Yikes. 0.75. 36, what's it say? To the nearest degree? Yeah, 39 degrees, or 37 degrees. Okay, yeah. To the nearest degree, in what direction should this? They should actually, if I was being really, being really picky, I could say north 37. What the heck am I doing? Jeez, oh Pete. Holy chicken nuggets here. North 37 degrees east. I was trying to be really, really picky about that. There's bearings here. All right. Couple more problems. I know. Stick with me, folks. Okay. Now, deviating again away from the unit circle. What am I looking at now? I'm looking for, how do I solve this equation? Sine theta is equal to 0.4. Now, notice that it's not capitalized, but I am restricting the domain. Okay. I'm restricting theta. I only want it to be negative 90 to positive 90. Okay, now, if I look for 0.4 on my unit circle, I'm not going to find it. So what I have to do is take this and see what happens. So let's do that. Inverse sine of 0.4 is 23.6. 23.6. And I boxed it, I should have made sure, is that within that restriction? Is 23.6 degrees within negative 90 to positive 90? Yes, it is. So you may be thinking, well, that was really easy. I just put it in my calculator. Sure. But what if you have this? We do the exact same calculation. We get the exact same thing from our calculator. So what are we supposed to do? Are we supposed to say no solution? Well, think about this. Obviously 23.6 is not within my domain of 90 to 270. Well, think about, what does 90 to 270 look like? Yeah. What does 90 to 270 look like? Well, 90 to 270 looks like 90. Here, I'll put it in a different color. 90 to 270. So what if I wanted it within that domain? Well, think about the rest of the unit circle. Your calculator, again, is a very dumb, smart object. What the calculator is calculating, and I did it on purpose, your calculator is doing capital sine. It's doing capital sine. So what do I have to do? I have to account for that. I know that the calculator is saying, okay, 23.6 degrees. That's the one that it's giving you. Okay. Where else is that? Well, think about this. This is y value, right? Where else along the unit circle has the same y value? Over here. Okay. Now, how do we calculate what that angle measure is? Well, this has the same reference angle here and here, because obviously angles with the same reference angle will have the same sines, cosines, and tangents. So if this is 23.6 degrees, this over here is 23.6 degrees. So how do I, reason that through? Well, if the reference angle is 23.6 degrees, I'm going to take 180 and I'm going to subtract away 23.6 degrees and see what I got. Is it a hard and fast rule that you always subtract it from 180? Absolutely not. You have to like logically reason through where it is on the unit circle and then go from there. So 156.4. This is the only other location along the unit circle where where the sine value is 0.4, where the y value is 0.4. Is that within our domain now? Is it between 90 and 270? Yeah. So I boxed that answer. That's my answer. Okay. Same thing here. Honestly, I could show you both of these. Because when I go to my calculator, like if I actually solve this equation, if I take, theta is inverse tangent of, and I should have capitalized that, -2, what does my calculator actually spit out to me? Inverse tangent of -2 gets me -63.4 degrees. -63.4 degrees. Is that within this restriction? Yeah, it is between -90 and positive 90. So that's my answer there. But the calculator is going to give me the exact same thing here. I sure hope that the other place where the tangent is -63.4 degrees, where the other tangent is -2, is in between 90 and 180. Now think about, where is 90 and 180? 90 and 180 is right here, right? That's the only place where I'm asking for. I'm restricting my domain to right there. If it doesn't end up right there, there's no solution in there. Okay, well, think about where -63.4 degrees is. There. Okay. Remember what I said earlier about tangents matching up. Tangents match up in diagonal quadrants, so that the actual tangent that's going to be there too is going to be over there. Does it fall within my domain? Yes, it does. Remember that look, we got some vertical angles right there, right? This is 63.4 degrees. This is also 63.4 degrees. So I'm going to take 180, and again, it's just coincidence that I'm subtracting it from 180. Okay, 180 minus 63.4 degrees is 116.6 degrees. Is that within my domain? Yeah, that's 90 to 180. Good. Let's do that one more time. Again, I'm going to grab this one here. Okay, so let's find it. Let's find the cosine. Let's say, okay, theta is, theta is inverse cosine of 0.3. Okay, so what is that? Let's go to our calculators and actually figure that out. Inverse cosine of 0.3 72.5 degrees. Is that from 0 to 180? Yep, so that's good. Okay, now 270 to 360. Think about your unit circle. Unit circle is, if I only want 270 to 360, here's 270, here's 360. So I only want down there. Now, think about where 72.5 degrees is. It's right here somewhere. I'm guesstimating. But the cosine value is 0.3. Think about this. This is 1/2. This is 1, right? So 0.3 would be somewhere around there. Where's the only other place with that x value? Right here. So it is defined. Okay, where is it? Well, it's down there. Let's figure out what the angle is. If this is 72.5 degrees, this is 72.5 degrees as well. So I'm going to take 360. I'm going to subtract away 72.5 degrees because that's the reference angle to figure out what my full true angle is. So I take 360 minus 72.5? 72.5. I get 287.5. 287.5 degrees, which is within my restricted domain. Man, that was fun. That was a great lesson right there. Hope we all had fun with me. Yeah, so I'll talk to you all later. See you when I see you.